Yeah, thank you, Professor De Donker, for the kind introduction. So today I will present about my PhD thesis with the title Horizontal Network Coupling for Charging Infrastructure based on three-phase solid-state transformers. And I would like to start with the European Green Deal, which aims to reduce EU-wide emissions to zero by 2050 and to achieve the 1.5-degree target and to reduce the climate change and global warming. So, and at the German and European level, we already achieved a lot of CO2 emission reduction. Since 2005, the emission trading was set up. And the latest predictions, however, say that we might not be able to reach the EU 2030 target, which is 55% emission reduction compared to 1990. And but looking only at Germany, there you see that we have a slight chance in actually achieving this intermediate target. And yes, however, if we take a look at the other sectors which are currently not part of the European emission trading system, then we find that we have a huge impact of the building sector and the transportation sector. And if we take a closer look at the transportation sector here, we find that 60% of these emissions are caused by passenger cars and motorcycles. So that means there's a huge emission reduction potential with switching over to battery electric vehicles and electrified transportation in general. So let's have a look at the current development in Germany. So today we have around 1.4 million EVs on the German streets, with some predictions that say that we will have between 4 and 10 million by the year of 2030. However, the governmental target is set to 50 million, but we might not be able to reach that with the current situation or with the current development of EVs on the market. And at the same time, also our government well understood that we need to invest in public charging infrastructure, as a large majority of people, especially in urban areas, really rely on this public available infrastructure. So today we have around 120,000 public charging points installed in Germany. And if we continue with that growth rate, then we will have around 320,000 charging points in the year 2030, with a share of 30% being DC, or also called fast charging station, and 70% AC charging stations. And if the charging infrastructure development continues or growth continues without the number of electric vehicles following, then we have, of course, the risk of a low utilization of public charging stations and thus a waste of the subsidies. So therefore, also the placement of charging stations or public charging stations is quite crucial to avoid stranded investments. And we also take a look at these top two topics within the Corona pandemic, because we cannot work, we're not allowed to work in a lab. So this was basically a side topic of my work. But if we look at the public and private charging infrastructure use cases, we find that on one side, we have a home charging or workplace charging, where typically the charging power is small and the charging process is long, and we have a large flexibility to schedule the charging processes to avoid peak loading hours. But at the public charging stations there, we have a peak charging power is increasing with the use cases from customer parking, road space parking, charging hubs, or high power charging stations along motorways. And therefore also the charging process duration is quite short, so we do not have any flexibility in actually shifting the charging processes to avoid some peak loadings or to have it coincidence with, for example, local PV generation. And therefore we have to guarantee that this charging power is always required, is always there, because the users will rely on this. And according to some projections, that we will need an on-demand public charging power of 23 to 32 gigawatts by the year of 2030. So now we can ask the question, what is the effect or the impact on our distribution grids with this development? Because initially they were not planned for that high peak or the additional loadings of charging infrastructure. So, and to understand this, we first need to take a look at the grid structure. And while our high voltage grids are typically meshed and n-1 operated, our classical distribution systems have a radial structure. And that means that we have a number of medium voltage transformers feeding different low voltage transformers, which typically just supply a single grid area. And the utilization of this distribution transformers here is typically quite low, with a load factor between 20 and 30%. But also, and especially in urban areas, we have a grid structure where we have those normally open points here in between the different neighboring transformers. And this is there to achieve a faster resupply during a fault or when you have a maintenance on one of the transformers. And we need to keep this structure in mind, because I will come back to that later. But what happens now if we install more EVs, or have more EVs, install more and more charging stations, then we are at the risk that these transformers will overload due to the high peak loading. And this is then typically associated with a lifetime reduction of the components, or even the destruction if there are some short circuits happening due to the degraded isolation materials. So typically, to avoid this situation, then we can just install new transformers or replace the existing ones with a higher power rating. But doing this, the average utilization of the installed transformers will remain quite low. And we tie up a lot of critical future resources, such as copper and steel, which are then purely utilized. So therefore, I will present today a power electronic-based load flow controller. This device, we call it the solid-state transformer. And this enables us to achieve a horizontal meshing of the grid by utilizing the existing structure and cable connection that is already there. And therefore, we can provide high peak powers at certain grid connection points by just distributing the loading among the neighboring substations. And we can also go one step further by using the same technology to build up a DC grid. And this is what we call an underlay DC grid. And this allows us to realize all the advantages of the DC grid, such as lower losses, lesser material consumption, simpler control, and increased efficiency due to the elimination of inverter stages. And in order to achieve this, we need a highly controllable and cost-efficient power electronics. And in the further course of this presentation, I will show how we can achieve this by using conventional and standardized power electronic building blocks. So the rest of the presentation is then structured as followed. So I will introduce the solid-state transformer and the necessary control structure. Then I will focus on the modeling and control of the three-phase dual-active bridge and the effect of a dead time on the steady state and dynamic behavior. And then I will present a novel anti-saturation controller for the DAB, and then finish with a conclusion and future work. So this is a prototype that we have. So we use a three-stage converter with conventional three-phase inverters and LCI filters at each grid connection site. And both inverter stages are then connected by a three-phase dual-active bridge or DC to DC conversion stage. And within this DAB, we use a medium frequency transformer with integrated series inductance, which you can see here or here in the picture. And its component has a rating of 250 kVA, 10 kilohertz, and weight only 50 kilograms. So it's quite handy. And we choose to have this approach with a galvanic isolation stage because with this structure, we do not have any path for circulating current that might occur, and especially during fault right through operation. We do not rely on controlling of some common mode voltages, so we can really eliminate the circulating currents and thus have a full fault right through operation. And further, since the control bandwidth of the DAB is quite high, we can also avoid any harmonic propagation between the two AC grids, which might not be the case if we use just a simple back-to-back converter. Yeah, on the top right here, you see the actual construction. So the whole setup was built by X-Control, and this transformer here is built by AQ Magnetics. So this is actually a product can be purchased as someone wants it. Now some more electrical parameters. So we choose typical low voltage IGBTs, 1.2 kilovolt devices, in order to be quite cost efficient. All stages operate with 10 kilohertz switching frequency, and the DC link voltage is set to 750 volt, but we can go up to 820. And for the three-phase transformer, it is rated for a switching frequency between 8 and 10 kilohertz. And we have a stray inductance of 19 microhenry with a turns ratio of 1 to 1, because here we do not need any voltage changes. So how can we control this device? So typically we have 5 control quantities, which are the 2 DC link voltages, the 2 AC grid, three-phase AC grid side currents of a primary and a secondary bridge, and then the phase shift of the dual active bridge, which is basically there to control the power flow. And if we choose this controller architecture, then we have a kind of a symmetrical layout. And this means that the DAB only acts as a disturbance to the active front end controllers. And if we just use this structure, then basically the dynamic behavior would only be achieved or set by the dynamics of the voltage controllers. But however, we can also use a predictive load decoupling. So we can calculate the output current of the DAB and feed it to the active front ends. And thus we can achieve our dynamic control objective, which is to eliminate any DC link voltage oscillations, also under very harsh load steps. So let's take a closer look at the controller structure. So for the active front ends, we have a classical cascaded controller structure with an inner current controller and then an outer voltage controller. And we can use a number of feed-forward measures or model sequence controls in order to optimize this active front-end controllers control. This is also part of my thesis, but I will not go further more deeper in this topic. For now, the only thing we need to understand is that if we want to use this predictive load decoupling here with basically this calculated reference current, then we have to guarantee that the transfer function of a DAB is always a unity, basically a unit delay over the complete operational area. And yes, also under non-ideal conditions. And to further motivate this, we can take a look at the simulation of a solid state transformer. So on top you have the DC link voltages, the grid side currents of the grid A and grid B on the secondary side. And then if we just apply a power step for the DAB, then you see that the output power here on the primary side basically depends on the reaction of the voltage controllers. So, and if we use the predictive load current decoupling, then we can actually achieve quite a fast power set point changes over the entire operation range. So, and this is and therefore we can have a fast and accurate current controllers, and the smooth DC link voltage during abrupt load step changes can be achieved. However, as I said before, we need to take a look. Can we actually assume that the behavior of the DAB can be always modeled as, like we call it, the ideal behavior, because it's just a simple delay? So let's take a look at the three-phase dual active bridge. So this is typically we have 3 phase legs which operate in block mode with a 50% duty cycle. And so we get this 6-step waveform here that is applied to the transformer. And if we now introduce then a phase shift between the primary and the secondary side, then we will have some current flowing and thus also some current on the DC side, which is just a rectified current here, which depends on the load angle phi and also the leakage inductance of a transformer and the electrical parameters of the system. And so the great benefit of the dual active bridge is that we can actually achieve also soft switching over a large operational area, which guarantees low EMI, but also high efficiency. Since we have just a rectified three-phase voltage here at the DC link, we only require a small DC link capacitance. And we can also model this dual active bridge in the alpha-beta domain. Therefore, we just apply the Clark transformation to the three-phase voltages. And with that, we get the 6 voltage vectors, depending on the switching state, for the primary and the secondary side bridge. And this can then be combined with the equivalent circuit of a transformer, where we only consider the leakage inductance and the magnetizing inductance. And then we can calculate the winding trajectory, which is basically the difference between the voltage at the primary side and the voltage at the secondary side. And then we find that this current trajectory is just a regular hexagon, which is also in steady state conditions centered around 0. And then we can further simplify this equation if we introduce a phase shift angle phi between the primary and secondary side. And then we get this quite handy equation, which depends on phi and also on the voltage conversion ratio. So now let's have a look at the actual impact of a dead time. So typically for every voltage source converter, we require a dead time, which is basically the time between the switch off of the first switch and the switch on of a second bridge in a phase lag. And we have to do this because the turn on and turn off times or slopes of the devices are not identical. So, and therefore we can prevent the bridge shoot through that would typically lead to destruction of a module. And the impact of the dead time on the dual active bridge depends on the switching frequency multiplied with the dead time itself. And if you then have, for example, a high dead time, then it could happen that your output power significantly deviates from the original equation, so the idealized situation. And as you see here, this is the control load angle. So in our case, large fraction of the usable control load angle is actually affected by that dead time. And that means that if we just use this feed-forward equation to calculate the reference current for the DAB, then we would make a large error, and this would then result in the situation that we still have some voltage oscillation on the DC link. So there can be different modes. We call the ideal mode, mode 0. Then here we have the mode 1B, where we have just a different slope. And we have a mode 2B, where the output power is actually not controllable by the phase shift angle. And to understand where this output power deviations come from, we can take a closer look at the switching transition for this mode 1B. And typically, so in here we are starting with a positive current, so the switch S1 is conducting, and then then we turn off the switch S1 here, so the current commutates to the diode D2 as it's decreasing, and then we can reach a 0 crossing of a current during the dead time of the primary bridge, and thus the output voltage will reverse, because then the opposite diode will start conducting the current. And this voltage reversal here with the time interval gamma causes then a reduction of the phase shift. So the effective phase shift that we apply is reduced. So, and in this case, we are not realizing 0 voltage switching, but somehow near 0 current switching, because this current can be around 0. However, the secondary side is still soft switched under this condition. And in total, there can be 8 different modes that can be derived by also combining the work from Benedict and Hoek, who also took a look at this. And there is also assumed an ideal switching behavior, so infinite magnetizing inductance, and also neglecting the winding resistance of the transformer. And as you can see here, we have different maps of output power versus phi for different voltage conversion ratios D. So different. So the ratio of the input to the output voltage is different. And then we see modes of a constant power flow, like here, here, here. And we have modes where we have a different slope. And also, whoops. And what we also see, and this is important when you, for example, want to use this DAB for a battery system, typically, then we can also have a power flow if your phi, control at angle phi is 0, but the voltage conversion ratio is unequal to 1. Because these are kind of things that need to be considered, for example, during startup operation. And we can also plot this modes then on a phase shift map, so we get quite a nice overview of the operating regions of the different modes. And we can also see if we increase the dead time when we have the similar switching frequency, then this mode 0, so the soft switching capability of the DAB is actually reduced. And when we then neglect the modes where we cannot control the output power by the phase shift, then we can draw this output power map where we actually see all feasible output powers. Actually, every output power is feasible for the different modes, and we can also calculate all different boundary conditions. So when we know when we want to apply a power reference, we can directly from this map identify the corresponding area and then use the proper output power function. Because for all of these modes here, we have then a different function of the output power independence of phi. So, and if we now consider all the different output modes, we can have different feed-forward functions. So in total here, we consider 5 different functions and combine this with the mode detection, which basically detects the output, the operating mode, and depends on the reference power and then the voltage conversion ratio. We can calculate the correct feed-forward angle and feed it to a modulator, and thus on steady state, we can follow the reference correctly. And we also achieved some good matching of these models with the measurements. As you can see here in this picture for 3 different dead times. However, we also had to consider the turn-off delay of the IGBT, which was 0.5 microseconds according to datasheet. So if we then subtract that, so we have basically our analytical dead time is reduced compared to the control dead time, and then we can get quite a good match with the actual reality and our model. So we just saw that we can now, for a steady state condition, identify always the correct output power. Now we'll have a look if we can also achieve this for transient conditions. So, and let's now consider that we want to have a phase shift, a load step from a power P1 to an output power P2. And both output power corresponds to the idealized mode 0, where we realize 0 voltage switching. So we look at the current in the alpha beta domains. We will first have this initial trajectory, and we want to go to this red trajectory, which is the target trajectory corresponding to phi 2. And we have Dr. Engel proposed years ago a method how to do this, and this is called the instantaneous current control. And we use here the 2-step method, where we just use 2 transient load angles to directly reach the steady state trajectory And this method proposes to have a first transient trajectory with the new load angle phi2, and then a second trajectory with the old angle phi1. So using this, we can directly reach steady state without any oscillation or DC bias of the phase currents. However, if we now want to have a power output step from a mode from a power P3, which corresponds to mode 1B to P4 in mode 0. Oops. Sorry, there went something wrong with the picture here. But what you should actually see is that these two current vectors are too short, because if we apply this proposed method, we have a voltage time area basically missing, and then we will end up not at this point, but somewhere here, and this means that we have an undershoot and unbalanced free phase currents. And in order to overcome this, we can calculate just different load angles that compensate this volt-second miss. And to do this, we firstly need to adapt the modeling of the DAB and alpha-beta components by introducing all the different modes. And it turned out that we can quite easily do this because we just have to consider the effective phase shift, which is reduced, or in this mode here increased, or in this mode 1A, it is a little bit more complicated, but effectively, as you can see here, the effective phase shift is also reduced. And if we now have the equations for all the different modes, then we can go back to the fundamental equation of the ICC and identify all the trajectories. Corresponding on the load angles and the output power. So we can first start with the initial trajectory. In our example, this is mode 1B. And then we need to identify the first transient trajectory, and this always corresponds to the initial mode. And the second transient trajectory can be of a different mode. So we have to do some kind of a case distinction because the second transient trajectory will depend on the sign of a current at the moment where we switch off the switch in the phase. And then the target trajectory depends again on the second load angle. And we can then write this equation and decompose it into real and imaginary parts. And if we solve this for phi T1 and phi 2, then we can get a closed form solution. So we now have load angles which can actually compensate the loss of the voltage time areas. And the good thing is this equation is quite handy, can be easily implemented on your DSP controller, but we have to do this for every mode change that can occur. So a lot of work to pre-calculate everything, but then again, we can just start on a DSP and apply just some simple case distinctions. And we can then also bring it all together and have a mode detection or adaptive feed forward. And then what I just presented, I call it the dead time compensated ICC. And yeah, oops. So, and if we then do a simulation in our case, for dead time of 2 microseconds, switching frequency of 10 kilohertz, you see that if we're using the conventional ICC here on left, we have a quite unbalanced current, and also can also see it in the current hexagon, which is not centered around zero and is always drifting. If we then apply the dead time compensated ICC for all the different output power steps, then the current will stay balanced under all conditions. And the same thing works, of course, on the hardware. Here I have an example of a step change where we use first the conventional ICC for a step change from 8 degrees to 16 degrees, and this corresponds to like 50 kilowatts. So you see for the conventional ICC, it is we have an undershoot followed by an overshoot and some oscillations. And with the dead time compensated ICC, we can directly reach here the target trajectory, and we only have very minor oscillations left. So let's come back to what we achieved. So we saw a method to compensate the dead time under steady state and also compensate the dead time under transient conditions. So this means that we can actually model the DAB as just a delay in a Z domain. Yeah, so the last topic I want to talk about is transformer anti-saturation controller, because this was also a major issue that we had to solve with our hardware from the beginning on. So first, what is transformer saturation actually? So this typically happens if we have a DC offset on our magnetizing current, and due to this DC offset, then we're operating in the nonlinear area of the flux linkage, and thus the main inductance is decreasing because the slope of the flux linkage is actually also different. And this then will cause typically some really high current spikes of the phase currents, because the magnetizing current and here the phase current is somehow a superposition. So in this DC component of the magnetizing current is typically associated with basically a DC voltage applied. And this can happen if we look at, like here, one phase lag, and we're switching a positive area A and then a negative voltage time area A dash. And if these do not add up to zero, then we can have a DC voltage applied to a magnetizing inductance. And then this will basically or consequently lead to or can lead to the transformer saturation. However, this DC component of the magnetizing current is only limited by the winding resistances. And if we have a high efficient transformer, typically our winding resistance is in the range of milliohms, and then we only require a few millivolts unbalanced, and then we can have quite high DC offsets occurring. So here on the left side, you see a measurement of the transformer, which is actually then here in saturation. So we first initially see the different DC offsets of the magnetizing currents, and then here at some point we are reaching some kind of threshold value, and then really the magnetizing inductance decreases, and thus the current increases rapidly. So, and we have seen a lot of measures also in the past how to detect this. One method was using the star point voltage and then determine the second harmonic of it to estimate the magnetizing current. However, since in our case the magnetizing current was in somehow a measurable range, or the DC offset of the magnetizing current was in the measurable range of our converter current measurements. Therefore, I utilized this to detect the DC offsets of all the phases by just sampling at the peak and valley of every phase during one switching period. And if we then add up those two sample points, we directly get the offset of the primary and secondary side. And if we add this up, then we have the DC offset of the magnetizing current. And typical controllers to regulate this is that we can just assume that if we manipulate the duty cycle of the bridges, which is typically 50% by just a small amount, then we can manipulate the voltage across the main inductance. And based on this principle, then you can create a controller with here the sampling, and then we get the DC magnetizing currents in we can transform it into alpha beta domain because then we only need 2 PI controllers and regulate this to 0. And if we do this, the control works quite good. So here you see initially a load step applied to the transformer. Then you see how nicely the magnetizing DC components build up. So you actually see this is quite a slow phenomenon because it's only related on the time constant of the transformer. And here at t equals 0, we activate the controller, and as you can see, we can well regulate the magnetizing DC offset to 0. However, if we're looking at the primary and secondary side offsets, we see that they're somehow opposing each other and they're not regulated to 0. And if you do this with at nominal voltage, we found that we can have quite high DC offset currents in our phase currents, which are opposing each other. That means that for the transformer, we have a DC flux cancellation, so we stay out of saturation, but we have now unbalanced phase currents, which is also highly unwanted because then we have different thermal, we have different losses of the switches in a phase lag and all that kind of problems. So what we want to achieve then is actually the trivial solution. So we want to have the 0 offsets of the magnetizing current and also of both primary and secondary side currents. So our initially system was then a single input, single output system because we just manipulated the duty cycles on both sides similarly. But we can also model the system, this transformer by just considering the main inductance and the 2 winding resistances, and then we see that we actually have a multiple input, multiple output system because we have the duty cycles on the primary side and the duty cycle on the secondary side that can be manipulated. So basically, we want to now control both offsets independently. And if we take a look at the transfer function then of the system, then we see that we have a strong coupling. So this is the coupling factor, which is probably above 1 Hertz. So without further methods, we cannot directly control the primary and secondary side DC currents independently. But we can introduce a decoupling controller based basically on the transfer functions, or this can be derived from the transfer functions of the state space matrix. And then we find that this is really a simple implementation because it is just a high pass filter. And with this decoupling controller here, then we can basically decouple the primary and secondary side, and we can consider both sides as just a single controller. So we can control one side without affecting the other side. So and here you see a comparison of the decoupled MIMO control and the initially ZISO control. And you see that for the ZISO controller, we have some opposing phase currents, while the MIMO control actually regulates the primary and secondary side currents to 0, and thus also the magnetizing current. And on the hardware, this also worked on the very dynamic conditions. So here we have brought some diagrams where we applied some harsh or some abrupt load step changes. And on the left side here, we are operating always in the area which is also affected by the dead time. We have here the DC output current, the DC offset of the magnetizing currents, primary side and secondary side. And as you can see, after some load steps, then we can have some quite high magnetizing currents, and the controller is individually regulating them to 0. And we're operating in the area which is corresponds to 0 voltage switching, so the ideal mode. Then we also find that we still have some DC offsets of the magnetizing currents, but they're not as large as in the area where we have the dead time. So we can also conclude from this that the dead time plays also a crucial role in this problem of transformer saturation that we typically saw in maybe all of our three-phase dual active bridges that we built. And also we can also do here a very a large load step by stepping from 30 to 20 degree, and you see that the controller can also handle this. So this works quite robust. Although what you could see sometimes is that the phase currents are a little bit dancing because our PWM resolution was somehow limited. But if we would have a higher resolution, then I think the control would be even more stable. So with that, I would come to the conclusion and the outlook of my presentation. So for the solid-state transformer, we saw that the horizontal meshing of AC grids using power electronics can actually help to reduce the peak loading. And this is also possible without changing the protection system of the current AC grids, because we do not have an impact on the short circuit power of these AC grids. So we can leave them as they are. And further, with this three-stage SST, so with a galvanic isolation stage, we can also enable a fault right-through operation, because typically also we want this kind of grid, grid applications that we just put it there, and it can work autonomously for a long time without any disturbances. And yeah, we also saw that a fast and dynamic power flow control without the DC link voltage fluctuation is possible. And with this control, I think we can in the future also go to setups where we have reduced DC link capacitors. So because the control can be so fast, we can reduce maybe 60 or 70% of the DC link capacitance that we had in our prototype. And for the DAB, we saw that we can compensate the steady state and transient dead time of the DAB with using this adaptive feed forward and this novel dead time compensated instantaneous current control. And also we can utilize the anti-saturation control based on the converter current measurements. So this is in our case also possible. And we can also achieve the DC phase balancing. And actually, if we use this DC balancing controller, then we could also ignore the instantaneous current control, because if we have DC offsets on the primary and secondary side, we can control them individually. So this controller also helps in the effectiveness of the instantaneous current controller to reduce just some current oscillations. And the future work would be definitely the field operation. We planned this, but unfortunately due to pandemic and time reasons, we were not able to do this for a very long time. And also a cost-benefit analysis would really help to understand the actual input, the actual benefit of these systems in larger grids. So we can also think about further design optimizations, so reduction of passive components. We could use silicon carbide switches. We could also try to use automotive inverters to build up the same system, because they're quite cost efficient, and also look at grid forming operation, maybe for some emergency cases. Typically, we will not rely on this, but it maybe would be handy to have this. And for the DAB, so currently the influence of a high magnetizing current on the dead time effects is always neglected. So there can be further modeling on this, and we could also think about an optimized or adaptive dead time, because now we just applied a single dead time, which might not be optimal for all the different switching transitions. And if we could use a adaptive dead time, then maybe we could also reduce the impact of this mode 1B, for example, that we saw, because we switch on a little bit earlier. And of course, efficiency optimization. So the efficiency of this dual active bridge was around 98%. So typically for IGBTs with 10 kilohertz, quite good, but still for grid applications, it might be a little bit too low if we compare it to a transformer, which is typically above 99%. And also some other modulation methods to have a reduced RMS current would also be of a high interest. And that, but I can say we also we have work ongoing on that topic at this moment. Yeah, and with this, I would like to end now my talk, and I'm now happy to answer your questions.